Welcome to demo session of FPGA based signal processing system. My name is Ranjan Tiwari and I will be introducing you to the Altera based FPGA boards, how it can be programmed and how simulation based programs can be deployed. And today in this session I will be using different hardware setups. So first I would like to introduce you to this hardware setup first. This is an NI Elvis board. This is the hardware prototyping board in which any analog circuits can be generated and its output can be given. It also has various control signals like LEDs we can get at the output also, and we can also measure signals through this banana cables and there are many functions, but we are using it for just for generating one deploying one analog oscillator circuit. Basically it is a buffer circuit and for getting the output. Another component is this FPGA board, which is Altera Stratix III FPGA board. So it has many peripherals like this is the DIP switch. These are the user configurable DIP switch. These are the push buttons. This is basically one of the HSMC card associated with this Altera board. This is the power supply, and from here this cable is going to the CPU through which it can be programmed, and it has the it works as a communication between the CPU and this board. Now apart from this HSMC card, there is also one more slot, so which is here. If I can remove this one, it can be shown. Yeah, this is one of the slot in which one extra HSMC card can be inserted. This is the DSO X2024 keysight oscilloscope. This is the also additional function of generating the signal through the WebGen. So we will be taking out this some of the test signals like sine wave, square wave through this cable, which is the we will be getting through WebGen function. And this it has 4 channels of measurement through the so through these probes we will be measuring the output of the output from the board or any signal. Now in today's session we will be looking into these various programs which are basically general DSP networks. Other than this also we will be also looking other programs like FIR filters, IIR filters and HDFT basically. So I will also would like to introduce you again to the how this DSP builder programs can be developed, and for it we have to install some softwares. So for this software, this is the basic overall package, Altera Complete Design Suite package. In this overall package comes 2 software, which is Quarters Complete Quarters, which has to be compatible with the MATLAB. So the compatibility has to be checked between MATLAB and this Quarters, whichever version we are installing. So the Quarters is basically a synthesizer which works as a synthesizing tool, which will be generating the HDL files which has to be deployed on the FPGA board. The DSP builder is the environment in which we will be doing these programmings. So like it is just like Simulink, where we do graphic based programming. So all the DSP builder programs which are in blue colors, it has the property of directly it can be deployed into the FPGA boards. So I will be also showing one of the basic programs, how it can be opened, how it can be saved, and then how a hardware file can be generated and it can be deployed onto the FPGA. So any DSP builder program can be opened in 2 ways. First, either I can open the MATLAB directly and create one of the DSP builder program, or if I have already some of the files saved on my desktop or computer, then I can directly open that file also. So let me start by creating one file, basic file, and how it can be saved. So let us say I have already opened the MATLAB. So the current directory on which I am working is C, and in this directory all of my files are already saved. First I have to open the Simulink. In Simulink, first I have to go to the Simulink and then I can open the any Simulink files. So from here I will be opening new file. So these are basically the Simulink basic blocks, which generally if you see commonly used blocks, these are like input output constant values, products and other values. All these blocks are generally in black color. But if you see when we install Altera Complete Design Suite, so it will be embedding these two tools basically, Altera DSP Builder Advanced Block Set and Altera DSP Builder Block Set. It has the general block sets. It is shown here. So it is categorized into various sub blocks, like all blocks here. We can see all of the blocks here, alt lab blocks, arithmetic blocks, whichever are there. So if I open any one of these, let us say I am opening arithmetic blocks. So it has all the arithmetic related blocks. So we can see that these blocks are basically in blue color. So it means that they are directly synthesizable on the FPGA. We have to compile it and then it can be synthesized onto the FPGA. So these are various boards like Cyclone boards, area boards and Stratix 3. So we are using Stratix 3 EP3SL150, which is the chip number. So I have already started opening, I have opened one file which is untitled. So either I can use both the blocks in this program, basic Simulink blocks or the DSP builder blocks. So if I have to search any block, then I will be searching, like, let us say input. So I will be getting the result from both the sites, like Simulink and Altera based. So these are the Altera based blocks, and this is basic Simulink blocks. So if I want to take some input values, or let us say this one input, no, not this one. Let me take the constant value. So I can take this one or this one also. If I right click here, it will be showing me add to untitled, because the latest file which I had opened was untitled. So I can click here, it will be shown here, and after that I can add any scope or display signal. So let us say I want to show it is a display. So these are the displays. This is the Simulink block. Right click and I can save it to auto. So it will be giving me the connections. I can do the connections like this one. This is one of the basic program. I can either save, but if I don't want to go for the hardware deployment, I can directly go check for the simulations, what are the simulation output it is giving. So I will be directly running, but the runtime I will be reducing like 0.02, and I can run this one. So we can see that the constant value has been transferred to the display. So I can save this one, or so let me save this file, save. So it will be asking me for the location where I want to save this file, and it will be saving this file as a .mdl, which is Simulink models. So let us say if I am saving it on the desktop, any name like my first DSP builder. Save. So this file has been saved on the desktop. Whenever I want to open, I can directly click on this file and it will be opening all these environments. Or I can go to the MATLAB and select the current directory, and I can go to this program and I can again work on this file basically. So I will be closing this one, since I have already made some of the files. So I will be opening those and I will be showing you the input and output related to that one. So the first program which I will be doing, like Integrator, which is the part of the general DSP network. It has already been taught in the lectures. General DSP network. This is the basic. This is the diagram of general DSP network. Discrete signal. So this is like general block in which by changing the coefficients like C1, A0, A1 and A2, V0, V1 and V2, we can get various type of filters also, and various different network also. So those networks are like moving averager or any filter, HDFT filter or comb filter or any oscillator. So by changing all these coefficients, we will be getting various networks also. So let me open one of the already made file, which is like first we will be doing the integrator. So it's integrator. So we can see these are the all the configurable blocks which has to be used for programming in DSP Builder. Below this one, this line, these are the used blocks. So if we can see, this is the ADC block which is already shown here. ADC2 I am using, which is a 14-bit ADC. It is again converted to bring it to the lower side, and then we are converting this to the, let us say if I am giving the sine wave signal, then I will be converting it to the square wave and then feeding it to the this overall block. So if we see, as I have shown in the PPT also, this is the comb filter and this is overall resonator part. So where it has the it has the C1 coefficients A0, A1, A2. So here also this is the comb filter part. The coefficient is, we are multiplying C1, and the resonator parts A0, A1, A2, V0, V1, V2. So by changing these values, I can get various networks. So right now we are working on the integrator. Whatever the signal I will be giving through the hardware to this ADC, I should be getting the integrated output. So let me first compile this one. I have already compiled. So it will be opening this one. Since I have already compiled, it has gone through all these steps like analyzing and then timings also, and then fitting and then synthesizing. So if my board is on, I will have to scan. It will be it has to detect the FPGA board which is already connected, Altera Stratix 3 EP3SL 150. So it has now detected the board. Now I can program it. So when I program, the developed program will be deployed into the FPGA board. So the input I have to give is like any sine wave signal which will be converted into square wave and inside this one, and it has to be like integrated. So the input will be, I will be giving like sine wave with which has the 20 or approx 20 kilohertz and 100 millivolt peak to peak signal. So for that I have to start the wave gen of this oscillator. So if you can see, the currently the frequency is 19.5 kilohertz and the waveform generated is sine wave. The current amplitude is around 283 millivolt peak to peak, which has some offset value also. So I will reduce this offset value to 0 because I do not need this right now. Yeah. So if I stop this one, right now the volt amplitude is high, so I will be making it somewhat lower. So 100 millivolt I will try to keep. So if we see, the yellow one is the input signal which we are giving, which is the sine wave signal, which has the frequency of right now it is somewhat noisy. So the input signal which we are giving is around 19.53 kilohertz. So it is after this one, when we pass the signal, it is converted into square wave. So which if you see here, first we are giving the sine wave signal, and then it is getting converted into square wave signal through this one, and we are directly feeding it to the DAC2. So which is DAC2, this is the DAC1, this is the DAC2, which is connected to the which is connected to the, I think this is the DSC 2, this is the DSC, I need, this is the DSC digital to analog 1, this is the DSC 1. So, this one, the square wave signal will be directly shown to D2A2, which is D2A2, this one is the D2A2, and if you can see this, this is like the, yeah, this is the blue one. So, the blue one is showing this signal, this one in the D2A2, which is nothing but the square wave signal, and after that it has to be integrated, and like if we integrate the square wave signal, it is giving me the ramp signal. So, it has been shown that any signal can be integrated and shown here. Right now I have taken the input as a sine wave, and it got converted into the square wave through this circuit. Like first we are using comparator, so whatever the signal sine wave we are giving, it is first giving 1 for any signal which is higher than 0, and then it is multiplied by 2 and it is converted into square wave, and then it has been given to D2A2 and D2A1. So, right now it is giving me this signal, and this is the integrator part right now, and I will be showing you the another program, which is a comb filter. So, comb filter, it has already been told that it is like a, it will be introducing n number of zeros into the signal. So, the characteristics, like whatever the frequency, fundamental frequency I have tuned it, like let us say I have tuned it for 20 kilohertz. So, it will first block the 20 kilohertz, and then further the harmonics like 20 to 40 and some like that. So, for this I will be giving any signal, and it should give me like blocking that particular frequency first, and then it will also block the corresponding harmonics also. So, I have already compiled this comb filter program. This is the comb filter. So, by changing these coefficients again, if you see, this is the part of the general DSP network. So, by changing these coefficients value, now A1 I am A0 I am taking 1, A1 is 0, A0 is 2, B0 is 1, B1 is 0, and B2 is 0. And this again we are using analog to A to D pin 2, and like I am getting the output from the right now I am getting the output from only one DSC, which is like DSC 1. So, this is the DSC 1, which is nothing but the DSC 1 is green channel. So, I have already compiled this one. So, Swiss comb filter, yeah. So, let me again check for the scanning. It has detected the FPGA board. Let me program. It has been programmed now. I will be selecting the appropriate input signal. So, if we see, we are using, since we are using only D2A1. So, D2A1 is this one, which is D2A is this one, which is passed to this green one. So, I will switch off the third channel, which is blue one. Now, what I am giving, it can be seen here through WebGen. The input is still 19.53 kilohertz frequency, having the frequency of 19.53 kilohertz, amplitude 100 millivolt, and offset is 0. So, I should be getting 0 at the 19.53, because if we see this mod is, it is counting up to 20, and it is trying to reduce the frequency. The clock frequency is 50 megahertz. If we see here, and 50 megahertz corresponds to 20 nanosecond of time. So, this is the time, this is the overall 50 megahertz clock, and we are trying to reduce this clock by counting more 20. It will be counting up to 20, and it will be after 20 it will give one pulse. So, what we are trying to do is reduce the frequency, so that the time will there will be a time delay, higher time delay. As the frequency reduces, the time will be higher and higher to match this comb filter property. So right now it gives me the sampling frequency fs signal. Fs is nothing but f into n. Whatever the f is the input fundamental frequency which I am giving. Let us say right now it is selected as 19.53, and if we divide this 50 megahertz by 20 and then again by 128, I will be getting around 19.53. So 50 megahertz divided by 20 comes around 2.5 megahertz, and then if I again divide that 2.5 megahertz signal with this 128, then I will be getting around 19.53, approx 20 kilohertz signal. So the fundamental signal becomes 20 kilohertz. It will be attenuating 20 kilohertz, around 20 kilohertz approx, and then 40. So the exact value comes around to be 19.53. So we can see currently the input is 19.53, and it is able to attenuate properly. If I try to reduce the signal from even from 19.53 to lower side or upper side, it will be attenuating. It will be passing, and it will be attenuating the fixed frequencies like 19.53 and twice a multiple of this one. So let me show by reducing this frequency or increase. So right now let me first reduce. So if I reduce, we can see that if when I am going from 19 to 19.53 to lower values, it is starting to pass the signal. As soon as I go around 19.53, it will be finally attenuating totally. Again, if I try to move on the higher side like 20, 25, it will start passing. So we will be getting the green signal. So it can be seen properly. Since it is running, it is somewhat noisy. So we can see that when we again go around 40 kilohertz, which is multiple of 19.53, so it will be around 38 point something. So if we go around that one, again it will start attenuating, and it will bring the output to 0. So I am increasing the frequency 36, 38. So we can see as soon as I go around 38 point, it again attenuates the overall signal. So this is I have shown the hardware implementation of the comb filter. So it will again, if I go higher, a multiple of thrice of 20 kilohertz. So again it will be attenuating, and in between those this fundamental and first harmonic and second harmonic, in between those it will be passing the signal. So the comb filter is complete now. Now I will be moving towards the moving averager, which is basically it will be giving me the smoothened signal of any input signal, or it will give me the DC signal. If I am passing any input signal having the DC value, so it should give me the DC, and it will attenuate all the frequencies. So this is the moving averager program. So I have already compiled these programs because it will take time. So if I open like compiler, this is the compiler. Since it has already been compiled and we have already detected the board, so no need to scan again. I can directly program. So I will be giving any signal which has certain frequency. Along with it, we will be adding some DC components. So this moving averager will give me the DC value, and it will attenuate overall the frequency, any AC signal basically. So it has been programmed now. So if we can see, the signal is given to A2D2, this one, and now we are getting the output around D2A1 again. So D2A1 is this one. D2A right now the D2A1 is this one, which is green one, yeah, which is green one, and the D2A2 is the blue one. So if I program, the input signal which I should be giving around some frequencies, let us say for it is 19.53 with the sine 19.53 kilohertz sine wave, 100 millivolt, and plus we will be adding some DC values around 10 millivolt. So right now the frequency is higher. I have to reduce the frequency. So I have not programmed. Let me first program this one, moving averager. Till the new program has been deployed on the FPGA board, it will be holding the older file. So before the programming of the moving averager, it was holding all the programs related to the previous one, like COM filter. Now since we have deployed this program, it has been dumped into the FPGA board. It should work properly as per our requirements of the moving averager. So I have not given right now the offset. I have to increase the offset value. So we will be giving around 10 millivolt. So this is the input signal currently is like the frequency. Let me select 19.53. So we can see that what the signal which I am giving with the DC, the program is able to extract the DC component basically and remove the overall AC signal. So the green signal, it is giving me a DC component only. If I increase, if you see, if I will be increasing, then it will pass these signals. So let us say I am increasing now. So it will pass the signals, but on this particular frequency only 19.53, it should give me the DC component only. .53. Yeah. So this is the input signal was signed along with some DC component, and the moving averager has been able to detect the or extract the DC component from the input signal. Now we will be moving to the another program, which is real oscillator. So real oscillator, by changing these coefficients only on the general DSP network, we get the real oscillator. So let me open first the real oscillator program. So this program has already we have made, and the coefficients are like A0 is 1, A0 is 1, A2 is -1, B0 is 1, B1 is equal to 0, and B2 is -1. So here I will be showing you that this is the overall oscillator program, and I can show you it will be generating some output. So here we are not using any ADC, and we are only using one DAC, which is D2A1, which is the green channel. Right now it has been selected as green channel D2A1. So I will be switching off the first channel now. So it should be able to give me the desired output. So this is like I have already told, this we are using to divide the overall clock signal, which this is the corresponds to 50 megahertz signal, and I am dividing it by 20, which comes around to if I divide by 20, it comes around 2.5 megahertz. And then it should if I divide it by n number of samples, let us say. So here we are giving n is equal to 128. So it should give me like around 19.53. If the you can see here we have given the 2 cos theta value, the n is 128. So it should be able to give me 2 signals like 19.53, and another one will be around which approx around 12 kilohertz. So it will be giving me some less than 12 kilohertz, because the sampling frequency it doesn't match exactly. So it will be giving somewhat less than the 12 kilohertz, which is approx 11.7 kilohertz signal. So this corresponds to 11.1 signal 11.7 kilohertz, which is given to mux on 1, and this is 20 kilohertz. Specifically saying 19.53 kilohertz, it is given to 0. So the overall program, if we can see by using the DIP switch, now I will be controlling the oscillator output. So I will be using only one switch of the DIP switch. Basically, these are basically 8-bit DIP switch. I will be using only the LSB, which is 0, and if it is 0, it will be selecting the 20 kilohertz signal, and it should be able to the oscillator program should be giving me the oscillator output of 20 kilohertz. And if I select it as 1, it should be able to give me the output frequency of 11.7 kilohertz. So let me compile this one. It is already compiled. So it has already been compiled. I will scan so that it will be detecting the board. It has detected the board. Now I am programming. As soon as it has been programmed, it has to give me the output. So we can see some frequency has been generated. Let me move it somewhat lower side. So we can see right now the frequency comes around 19.5. 19.53 kilohertz. Why? Because the switch, if we can see, this is the switch is on the 0. So this DIP switch we can see, if it is moved toward this one, it is 0, and if I move this DIP switch to this side, it corresponds to 1. So right now it is at the position of 0. So it is giving me the frequency of 19.5 kilohertz. As soon as I change this DIP switch from this position to the position of 1, it will be changing the frequency. So let me now select this one. So we can see, as soon as I change this DIP switch from 0 position to 1 position, it has been able to change the frequency, and it is coming around 11.7 kilohertz. So we can see properly the output has now moved from 19.53 kilohertz to 11.7 kilohertz. So this is the overall oscillator program. Now I will be moving towards the another program. So the other program is FIR, low pass filter. So FIR low pass filter, this is the FIR low pass filter program. So this is the, again we will be using ATD2, and these are the coefficients associated with this low pass filter. So it will be cutting the signal around 1 megahertz. These coefficients are corresponding to that one, and the below that frequency, it will be passing all the signals. So since I am using this A2D already, so I will be switching on this first channel, whatever the signal I am generating, and then since I am using D2A1, so which is the green channel only, so I don't have to switch on blue one. So since I have already compiled to save the time, the board has already been selected. Now I will be programming. This is the FIR program. So it has been programmed now. We can see the current generated signal is WebGen. If I go to WebGen, currently the frequency selected is 19.53 kilohertz, and it will pass up to approx 1 megahertz. I will show you quickly. The yellow one is the input signal and the green one is the output signal. If I keep on increasing the frequency, right now it has moved around 70 kilohertz. Now it is around 90 kilohertz. It is now 630 kilohertz. Now it is around 800 kilohertz. As we go around 1 megahertz, it is seen, it starts attenuating. So it is suppressing those signals, any signal we approx around 1 megahertz. So you can see is if I move around approx 1 megahertz, and below that frequency, it will be passing the signal. So I have shown you the FIR low pass filter uh, through which I have also deployed on the FPGA board. This is the overall program. So these are the coefficients related, which I have already told: C1 minus 1, C2 3.75, C3 3.75, and C4 minus 1. So these are the three delays, and these are the coefficients related to this low pass filter. Now the next program is IER filter. So till now I have shown you all the programs there. I have shown you on hardware how it can be implemented on hardware. Here I will try to introduce you how it can be done on simulation also. In hardware, sometimes there are many constraints. Sometimes output will not come if there is any change in the input, or any very slight, even slight changes can give me the erroneous output. So IER low pass filter, we will be doing the simulation quickly. IER low pass filter. This is the program. So we can see this here the blue boxes along with black boxes are also used. So if this program is not directly synthesizable on the FPGA, I have to remove this black box if I go for hardware implementation. But here I am only showing the simulation. So we can see the input which I am giving is like the combination of two frequencies. One is 1 kilohertz cos 2 pi k, so which is like 1 kilohertz, and the second signal is 10 kilohertz. So since it is a low pass filter, it will be passing the lower frequency which is 1 kilohertz, and it should be able to give me the output of 1 kilohertz, and it should attenuate the higher frequency which is 10 kilohertz. So this is the RAM signal which is working as a time. So it continuously increases and it generates this signal. So let me run this file. These are the coefficients related to this IIR filter. So now I can open the scope. So we can see the upper row or upper scope. The input contains two signals, which it is the combination of two signals, 1 kilohertz and 10 kilohertz. But when we are extracting, so if you see, this is the output we are extracting on the second trace. So it is able to give me the 1 kilohertz output, and it is able to eliminate the higher frequency. So if you see, the time period comes around 0.001, which is nothing but the it corresponds to 1 kilohertz. 1 by 1 kilohertz, it comes around to be 0.001. So I have also shown here the IIR filter implementation, and I have shown how it can be done on simulation also. If I have to go to for the hardware implementation, I have to remove this black box, and I have to add ADC, DAC, or however I want to implement this program. So IR filter is complete again. Now the HDFT, it has already been taught in the lectures. HDFT is the one of the extended version of the SDFT, which is sliding discrete Fourier transform. HDFT is hopping discrete Fourier transform. So I will be giving input signal, and it should be able to give me the extracted in phase and quadrature phase. So this is HDFT program I have already compiled also. So we can see again I am using the ADC2, and I am now using both the DAC of this HSMC card. So DAC1 and DAC2 also. So in DSC1 I should be getting the in phase component. Basically this is the overall HDFT program. First what I am trying to do is, first I will be giving the input to this ADC, and I am converting it to the square wave, and then this is the filter part, this is the filter part, COM filter, and this is the overall resonator part. And again this one is generating the sampling frequency, so which I have already told, like 50 megahertz divided by 20. So it is reducing the frequency and it is giving me the sampling frequency, which has to be from this one, it has to be fed to all the delay blocks, like it will be working as an enable signal. So let me generate this signal, and I will be selecting the third channel again also. Since I have already compiled this one, so this is switch HDFT2. It has already been compiled and the board has already been detected. So I will be directly programming. As soon as it gets programmed, it will be giving me the it should give me the output. So currently the sampling frequency selected is for the input signal of 19.53 kilohertz. Let me reduce this offset. I am keeping it at 0. The frequency is higher, that's why it is not able to give the output. Let me go to the fundamental frequency, which is 19.53 kilohertz for this program. So as soon as I move towards that frequency, I am starting to get the signal. Let me match this 19.53. Yeah. So right now I am giving the input signal of sine wave and having the frequency of 19.53 kilohertz, which has the amplitude of 100 millivolt peak to peak. So let me stop this one. We can see these are the three signals. The yellow one is the input signal, and the green one is the extracted. The first one is this I have to invert. So this is the extracted in phase signal. It should be able to if I try to match the yellow one and green one, it should be matching. If I do this, yeah. Yeah. So the first channel is the green one, which is the in phase component, and the second channel is the blue one, which is the quadrature phase component. So whatever signal I am giving here, right now it is it has the fundamental frequency is tuned around 19.53. So it is giving me the extracted in phase and quadrature phase component of the input signal. I can run again and I can show you. The yellow one is the input signal, which is fed to the ADC, and then the green one is the in phase component, which is shown on the green channel, which is shown through this D2A1, and the this is the quadrature phase component, which is shown over the blue channel. So this is the overall HDFT program, and I have shown that it can the input signal can the fundamental frequency of the any input signal. The signal could have been the square wave also, and its fundamental frequency can be extracted. So let me again also show by changing this signal to square wave signal. So even if I change the signal from sine wave to square wave, it should give me the output. So right now I have changed to square wave. So we can see the input signal has been changed from sine wave to square wave, but still it is able to extract the fundamental frequency, and the it has on the green channel it is the in phase component, and on the blue channel the quadrature phase component has been extracted. So apart from these programs, I will also like you to introduce you to the some of the available functions on the of the DSP builder, like FFT. So in the DSP builder, it has already been given like core FFT IP core, so which can be also be used for programming FFT. I will basically only show I will just show you the how it the cores are shown on the DSP builder. So let me move here. Simulink. Let me open any Simulink block, Simulink program. So let me open some Simulink. So here we can see in the Altera DSP builder advanced block sets. These are the FFT based blocks which are already available on this. It can be explored. The FFT can be programmed. So these are the FFT based programs like Redx2, and all the functions are already there. So it can be used to do the programming for the FFT also. So this is from my side. I have shown you all the some of the programs like Integrator, Con filter. Then I have used moving averager, real oscillator to generate different signals on the hardware. I have shown FIR filter, FIR low pass filter, which was basically IR filter, on which I also showed you how to do the simulations. And then HDFT, which is the hopping discrete Fourier transform. It is somewhat the extended version of the sliding discrete Fourier transform, HDFT. So this is it from my side. Thank you.